Okay, let's see who we have online now. Okay, hi Juliana. I think you can probably hear my voice, see my screen right now. If you can, just type into the chat box so I know things are working. Oh, maybe not. Oh, I see what the problem is. Let's see. Show screen? No, it should be showing my screen. Hello out there in TV land. Chat box is in the that little control panel, and it's at the very bottom. You might have to turn that little triangle down in order to see it. Ah, great. I'm not sure that I'm reaching you, but we'll get started in a minute. I'll wait to see if we get any more attendees. It's early in the morning, and it's tough to do this kind of stuff on a weekend, right? Oh, it's working. Okay. Let me see what I can do here to make sure that I am connected. Okay, still waiting for some more attendees and to hear from Juliana. If you can type into the chat box if you can hear my voice and see my screen. Actually, I'll unmute you for a moment since it's just the two of us here. Okay, let me know if you can see my screen and hear my voice. Okay, well, I'm going to go ahead and get started and see where we go from there. Presumably, you have some people dropping in. I'll mute that microphone. And remute my microphone here so I don't get feedback. Okay, so well, make a long story short, I got a lot of questions about the homeworks. Well, not a lot. Let me rephrase that. I got a number of questions about the homeworks. Some of them had some common elements to them. It helps a lot when people are specific and let me know when, which particular problems or which topic areas that are, causing difficulty, because I then can go back and concentrate on those. I got a number of people that were talking that let me know that they had issues with specific problems. I'm going to try and answer those as much as I can now. However, sometimes when you got to be as specific as possible, because for instance, if you tell me that you have a problem with the question number 8 on the homework and there's 2 assignments and I'm not sure which assignment you're talking about, then I can't go back there and tell which one that you're having an issue with. So I think in general, I'm going to try and make sure I cover these and go over the homeworks in general. It would even help if you just type in, copy and paste in to your comment in the discussions board. The elements that are problem that we need to work with, because then I don't have to go chasing it and stuff like that. Okay, so I'm going to go ahead and get started, and I'm going to start with assignment number 4. I'm going to work my way through these problems. Some of them I'll help you solve. Some of them I'll leave for you to solve, and I'll just give you some background on them. Among adults in the United States, the distribution of albumin levels, tryptophan, and cerebrospinal fluid is roughly symmetric, with a mean, in other words, normal, with a mean of 29.5 and a standard deviation, sigma, of 9.25. So here we've gotten the population mean and we've gotten the population standard deviation. We already know everything there is to know about this population, basically, as far as normal distribution is concerned. So clearly this is not a sample. It's completely about a population. So what would you mean? What would you expect the mean of the sample means to be? In other words, if you took one sample from this population, whatever size, and you took a second sample from this population, whatever size, you took a third sample, if you took many, many samples from this population, and you took the average of all the sample means that you got, what would you expect those to be? Well, you'd expect it to be the same as the population mean, right? Sometimes you would get your sample mean would be lower than 29.5, sometimes it would be higher, but it would be equally distributed between the two, assuming the population is normally distributed. What would you expect the standard deviation for the repeated sample means to be? Well, let's see. That's a little bit trickier, isn't it? If we looked at any individual sample, the people that we would get from that sample group would have the same variability as the population would have. So the sample distribution approximates the population distribution. Sorry, I got a little bit of a frog in my throat this morning. So that would approximate the same standard deviation as the population has. But that's not what this question is asking. This question is asking, what would you expect the standard deviation for the repeated sample means? In other words, took a sample, got the mean, took a sample, got the mean, took a sample, got the mean, and then you took all of those averages and made a new distribution. What would be the standard deviation of that new distribution? Well, now that would not be the same as the population, right? The individual samples what standard deviation would be, but this new mean, the mean of these repeated samples would be equal to the standard deviation of the population, sigma, divided by the square root of the sample size, whatever that sample size happens to be. Okay, now in fact, I did give you a sample size to work with, so that helps. What's another name for the standard deviation of the sample means? Well, we know. We like to call that by its own given name. I'll leave that up to you to remember. You can look that up if you don't remember. I'm sure you guys remember that one by now. What proportion of the means of the samples of size 20 are expected to be larger than 33 milligrams? What proportion of the sample means are expected to be less than 28 milligrams? What proportion of the means are expected to be between those two numbers? Okay, so let's take a look at what we're going to do here. So we're looking at the means. We're looking at the means of the samples themselves, not the population, but the means of the sample. So I'm going to sketch that out. Whoops. If I can't get to my pad here. Okay, first thing I'm going to write up here is I'm going to, just so I can remember it, I'm going to say to myself, okay, the mean for the population is equal to 28.9, if I'm correct. I'm going to go back and check that. Oh, 29.5, sorry. Let me go back here. See if I can erase that. Okay. Is equal to 29.5. And the standard deviation for the population, sigma, is 9.25. Okay. So if I've sketched that, the population would look something like this. Mean would be 29.5, and the standard deviation would be 9.25. Okay, so 95% of the population, the actual people, the population, 95% would be roughly about, I'm going to add that 9.25 to 29.5, and I'm going to call it 39. Roughly about 30, roughly, and I'm going to take it away. That's going to be roughly about 20. 95% of this population is roughly going to be between 20 and 39. That's population. How about now if we take a sample of size n equals 20? Okay, well now we have a whole different situation. Now we have, and we take those repeated samples and we draw a new distribution, right? Well, we expect the sample means, the repeated sample means, to be the same as the population mean, 29.5, but the standard deviation of this of these sample means is, we're going to call it standard error. Oh, gave that one away, right? Standard error is equal to the standard deviation of the population, which is 9.25 sigma over the square root of the sample size, or 9.25 over the square root of 20. Now I'm going to leave you to figure out what that number is, okay? But that's going to be your standard error. Okay, so I think that was one of the questions there that we had to answer, right? Standard error. So now the next question, actually, I'm going to have to figure it out because I need the next step. So I'm going to do that. (9.25), right? First, let me do the square root of 20. Square root of 20, I'm going to put that into memory. 9.25 divided by the square root of 20 is equal to 2.06, 2.07. So I'm going to call it 2.07. 2.07. Okay, and let's see, we got 2.07 is our standard error. So now the question was, let's go back here. Let's see. What proportion of the means of the samples, size 20, you expect to be larger than 33 and less than 28? Again, always helps to sketch this stuff up. Larger than 33 and less than 28. That's 28 and that's 33. So what percentage do we expect to be larger than 33 and less than 28? Okay, so how are we going to solve that? Well, we need to know what z-score is represented by the number 28. And we can that's the number of standard deviations in the case of the sample means, that's standard errors. It's the number of standard errors below the mean that this value is and above the mean that this value is. So this value, number of standard errors it is, let's see, it's an even number, it's going to be 1.5, but our standard error is 2, so it's not going to be a nice even number, so I'm going to ignore the empirical formula for sure, right? So I'm going to calculate z. Z is equal to, is the number we're interested in, x minus mu over sigma, which is equal to 28 minus 29.5 over the standard deviation, which is 2.07, right? So that's kind of, the z-score there is going to be, let's get our calculator back. It's going to be 1.5 divided by 2.07. See, now I could have not just kept that in memory, not have to round it and stuff like that. That would be best. Okay, so that the z-score there is 0.72. I'm just going to call it 0.72, round it off there, is equal to 0.72. Okay, now what about the z-score for the other value, the 33? That's going to be equal to, let's see, that's going to be equal to 33 minus 29.5 over 2.07. Okay, see what that comes out to. Okay, that's going to be 3.5 over 2.07. Now this is going to be a negative number, right? Because x is smaller. Oh, excuse me. It's going to be a negative number because x is smaller than the mean. It's going to be a positive number. Okay, so 3.07. 3.07 divided by 2. No, excuse me. 3.5 divided by 2. Got to clear that. 3.5 divided by 2.07 is equal to 1.69. Okay. Okay, so now I am going to go to my table, my z table. Okay, now you can use the z table because I am working with I'm working in a situation where I know the population standard deviation. Even though it's a small sample, I know the population standard deviation. So I'm working with the z table. Okay, so I'm going to go here and I am going to here, and z table is negative 0.72, negative 0.7012. That represents an area of 23.58, 0.2358. 0.2358 or 23.58%. Well, how about this other area over here? How about my z-score of plus 1.69? Okay, what area is that going to be represented here? Well, remember that the table always gives you the area from here down. So the area from here down is 23.8, that area in there. Now this is going to give me the area from here down, which includes this area in here and the area we just looked at here. So I have to keep that in mind because I really want this area greater than, right? So I want to go to 1.69, positive 1.69. 1.6, and I got it all the way across there. 1.69 is going to be 95.45%, 0.9545. 0.9545. They didn't really do that good a job of drawing this in perspective because it's really only about that much of it that's left. Because we can see that it's almost 2 standard deviations over, so I should have gone a little bit further. Okay, so anyway, so now the percentage of the population, the proportion of the population that's less than 28, has serum cholesterol less than 28, is 0.2358. The proportion of the population that has a serum cholesterol over 33 is not going to be 95. It's going to be 1 minus 0.9545, okay, which is going to be equal to, I'll do this quickly, 0.0455, I guess, right? 5 carried 1, yep. About 4.5% of the population is going to be represented here. Not very well drawn. Okay, and the next question would ask you, well, what's the probability that you would have serum cholesterol between 28 and 33? Well, that's going to be the area in here. And how can we calculate that? Well, it's 100% less this, less this. So if we add these two areas together, right, and then subtract it from 1, we'll be left with the area in between. about 23.5%, and 4.5% give us about 28%. So that would leave about 62%, 72% of the area in between those two numbers. Okay, and basically all these problems work out the same way when you're dealing with the repeated samples. There's going to be a big difference when we don't know the population standard deviation, but we're going to be getting to that as well. Okay. Okay, let's see how we're doing here. Let me just make sure that I got my paperwork right here. Okay, let's see. Just want to make sure that I'm not leading you astray here. Okay, let's move on to the next one. Let's see. Where's this start? In Denver, Colorado, the distribution of daily measures of ambient acid gases slightly skewed to the right, with a mean of 1.61 micrograms per cubic meter and a standard deviation of 2.25. Big standard deviation there, right? Based on the central limit theorem, the distribution of sample means of size 100 is expected to be skewed to the right, skewed to the left, normal, or bimodal. Let's think about this. Based on the central limit theorem, what does the central limit theorem tell us? The central limit theorem tells us that we would expect that even if the initial population is not completely normally distributed, that repeated sample means taken from that population will be normally distributed, at least well enough normally distributed for us to apply our knowledge of the normal distribution to it. Okay, and the bigger the sample size gets, the greater that the skew that it will correct for, the central limit theorem. Okay, so in this case, we can say, well, yeah, we're going to work with central limit theorem because the distribution of the means with nice sample size like 100 is going to be fairly normal. So we're going to be able to, we can expect it to be normally distributed. The standard deviation of the sample means size 100. What's the standard deviation of the sample means? Standard error. What's that equal to? We know that's the square root of the standard deviation of the population divided by it's the sigma, the standard deviation of the population divided by the square root of the sample size. Sample size is 100. Square root of 100 is 10. So standard deviation of samples, the standard error, is 2.25 divided by 10, and it's going to be 0.025, right? So that's our new standard deviation, new standard error, 0.025. What's the mean of the sample means expected to be? If you took a sample of 100 times over and over again, what would you expect given the central limit theorem? What would you expect the repeated samples of size 100? What would you expect the mean of all of those samples that you took to be? And we would expect it to be the same as the population mean. Okay, standard deviation changes because you're averaging and you're getting all the values. You're going to get it closer to the mean, so it's less of a spread. But the population mean stays the same. It's going to be 1.61, right? Okay. Okay, let's see. The probability that an infant is born prematurely in Mexico is 0.15. Now, the only difference here now is our point estimate. Instead of being a mean, numerical mean, is going to be a proportion. Okay, so what's the standard deviation for the proportion of premature births if we were to take repeated samples? If we know that, actually we don't normally know that, but if we know that that's true, what would we expect the standard deviation, standard error in other words, for the proportion of premature births in Mexico to be if we kept taking samples over and over and over again? Okay, so and those sample size happens to be 25. Okay, so that's a pretty small sample size, but if we know the population proportion, that's like knowing the standard deviation for the population. So we don't have to worry about the sample size if we know what the true population proportion P is, right? So we know that that's going to be equal to the square root of p, which is 0.15, times 1 minus p, which is 0.85, divided by the sample size, which is 25, and then we take the square root of the whole thing. Okay, so we can only use that sample size, that smaller sample size, because we know I've been told what the true population proportion is. And so I can calculate the standard error if we were to go through the exercise of taking repeated samples from here. A little bit of a twist on the problems, but most of the time the problems are going to look more like what we're about to see next. Okay, so we expect 95% of the portions for samples of size 625 to be between what two values? So we're looking at this same situation, right? Where we have our proportion, right? We calculated our standard error. Okay, I'm going to do that again. I'll do that again on this paper. Okay, so 0.15 times 0.85 over 25, right? And I take the square root of that. Except this time, hang on a second here. This time we're going to be working with a sample of size 625. So it's going to be different. The standard error is going to be different than it is here because we're working with a larger sample size. It's in fact going to be a considerably smaller number. So this is going to be 625 instead of 25. So let's calculate that. Okay, here's my calculator. Whoops, where'd it go? Let me try and get it back. Let me quit. Make it come to the front. And I still lost it. I think it's behind my control panel. Yeah, there it is. Okay. I couldn't see it because it's behind my control panel over there. Okay. So we have we have at least one other person that logged on now. Hello, welcome, morning. And if you can type into the box to make sure that you can hear me and see my screen, so that I know that things are working online, and I'll continue. And if you have any specific questions, you can type in there as well. Okay, so I'm going to go ahead and do this. 0.15 times 0.85 divided by 625 equals that. Take the square root, and we get 0.014 roughly. Okay, again, better if I don't round. So I'm going to go ahead. This is equal to 0.014. So that's our standard error. 0.014 is our standard error for this proportion. Okay, this is recording, so if you arrived now, you could always go back and watch this again later on and catch up on this particular problem. We would expect 95% of the proportions for samples of this size to be between this number and this number. In other words, what's our 95% confidence interval? Just another way of saying what's our 95% confidence interval. Well, we know we've calculated for our, we needed to calculate our standard error to answer that question. So that's our standard error. So now we're going to actually calculate what our distribution, what our confidence interval is. Okay, so for our proportion, our confidence interval is going to be 0.15, right? In other words, p cap, p cap, plus or minus 1.96, because we're using the z-score here because it's a very big sample. Okay, and I think we actually can, actually in this case, we actually know the population distribution. So we can actually, even if we're a small sample, we could have gotten away with that. But normally, you wouldn't be told what the population proportion is. You'd be taking a sample to try and figure out what it is. Okay, so plus or minus 1.96 times our standard error, which is 0.014. Let's calculate that. Okay, I'm gonna let's see, I'm gonna multiply. I already have this here, so I'm gonna multiply that by 1.96. Sorry, my calculator. I'm going to store it. Let me clear that out. I'm going to store it in memory. I'm going to hit clear. I'm going to say 1. I'm sorry. PCAP was 0.15. 0.15 minus my margin of error, 1.96 times 0.014, is equal to that. Okay. Whoops, I think something went wrong there. Okay. Let me try that again. Let's try it from scratch. Okay, so 0.014, 1.96 times 0.014. Okay, that's my margin of error now. So I'm going to put that into memory. Kind of lost track of that a little while ago. Okay, so now I'm going to take PCAP, which is 0.15, minus my margin of error. In other words, 0.15 minus this margin of error. Okay, minus this is equal to 0.123. Okay, going to round that off a little bit for practical purposes. Let me just put it where I can reach it. 0.123, comma, and the upper limit for our confidence interval is going to be, 0.15 plus our margin of error, which is going to be equal to 0.177. 0.177. So that's our 95. That's where we would expect, since we know what we've been told the proportion for the population. We know if we take repeated samples of size 625, that 95% of the samples, I use the z-score for 95%. Okay, 95% of the samples are going to be between 0.123 and 0.177. Kind of a little bit of a fake situation, because you normally don't know what this is. You're taking a sample and trying to determine what it is. Okay, but in this case, we know what it is, so we can actually calculate where we would expect 95% of repeated samples of 625 to wind up being. Okay, so let's move on there. I think that's it for that particular homework. Let's go to number 5. Okay, number 5, we actually start to apply this this confidence interval stuff. Okay, and I tried to make it a little bit more interesting and use a Halloween theme. And since for some reason zombies have taken over Halloween, I guess the popularity of some of the TV shows they're on now. But it's become a real cultural thing. I mean, I remember vaguely when the really first big popular zombie movie came out, Night of the Living Dead, and I mean zombie movies and science fiction interests were kind of kind of around, but they hadn't taken over like they have now. I mean, it's really kind of become a real phenomenon. But at any rate. Okay, zombie pyramid. This is a zombie food pyramid we have below here. Obviously, they eat a lot of brains and stuff like that, nervous system parts. But that's their main meal, and they don't like bones and stuff like that very much. Serum cholesterol. So that you got to wonder what their cholesterol level is like. A lot of organs and stuff. You eat a lot of organs. Serum cholesterol levels are measured in 25 randomly selected adult zombies. Assuming you can find them to stand still. They're slow, so you can get samples pretty easily. I found 25 randomly selected zombies. The mean of the samples is found to be 151.4. The population standard deviation for zombie serum cholesterol is assumed to be the same as it is for living humans, which we know from very large studies is 38 milligrams per deciliter. Okay, so we're saying we know what sigma is here. So we took a sample. Sample size was 25. But if that's all we knew, we would have to calculate the standard deviation, estimate the standard deviation of the population from the standard deviation of the variability of the people we sampled, the zombies that we sampled. Okay. So in this case, though, this case is a little bit unusual situation. We're assuming we know the population standard deviation. That means that even though it's a small sample, we can use the Z table instead of the T table. So that's the key. Number one, do you know the population standard deviation? If you do, you're working with Z. If you don't, then you're working with standard deviation you have to derive from only your sample, and that means that you have to calculate your standard error from standard deviation of your sample instead of sigma over the square root of n, and then you're forced to use the T table, unless you have a very large sample. And a lot of people define a large sample as many different things. Some textbooks you'll see it as greater than 30. Some other textbooks it'll be 100. But the real key here is that really that anytime you use the Z table when you don't know the population standard deviation, it's a little bit of a compromise. So basically, what we're saying is that when we have a big sample, even though we don't know the population standard deviation, we'll use the Z table kind of as a cheat. And it's less of a cheat the larger the sample is. Okay, so long story short, if you know the population standard deviation, you use the Z table. If you don't know the population standard deviation, you use the T table. And unless you have a very large sample, in which case you might be willing to cheat a little bit and use the Z table instead of the T table, even though you don't know the population standard deviation. So let's go ahead and solve a couple of these things. I hope that clarified things rather than it made them more confusing. Calculate the standard error for zombie cholesterol for sample size of 25 and known population sigma. Okay, let's go ahead and calculate that. Okay, so let's see. Let me get a fresh piece of paper here, or or electronic paper, whatever it is. Okay, so this is going to be, let's see, our population, our serum cholesterol, our means, our let's see, that was a sample, I think, right? Oh, first we want to calculate standard error. So the standard deviation for humans and zombies is 38 milligrams per deciliter. I'm going to ignore the milligrams per deciliter. I'm going to might as well put it in. Okay, that's the standard deviation for the population. So the standard error for repeated samples of size, what size did we say? Size 25? The standard error, if we take repeated samples of size 25, or a sample size of 25, standard error is equal to sigma over the square root of the sample size is equal to 38 over square root of 25. Square root of 25 is 5 over 5. And that's going to be equal to 6.3 fifths is 6.6. Right? Right about that? Yes. I am right about that, I think. Yes. 6.6. Okay. So let's move on from there. Calculate the lower value for 95% confidence interval for the mean cholesterol for all zombies. The upper value, calculate the lower 90%. We want to calculate the 95% confidence interval for serum cholesterol for zombies, 90% confidence interval, and the 99% confidence interval. So basically, we want to calculate all confidence intervals. So I'm going to set this up. I'm not going to actually solve them, but I'm going to set up the numbers, and you can go ahead and solve them. So how are we going to do this? Well, the average serum cholesterol that we started with, the mean serum cholesterol that we started with, was a sample of size 25, and the mean of the sample was found to be 151.4, right? 150, and the mean, X bar, the mean of the sample is what was it, 151.4? 151.4, right? And my sample size was equal to 25. Okay, and we just calculated that our standard error is equal to 6.6. So how do I calculate my confidence interval? Well, my confidence interval is going to be equal to x bar, my sample mean, plus or minus the z-score that I'm going to use for my confidence interval, that's appropriate for a confidence interval that I want, the width of the confidence interval, times my standard error. Okay, times my standard error. So where we're talking about a 95% confidence interval, and I'm using z here because I know sigma, right? I calculated my standard error from a known sigma. I know the population standard deviation. So I'm going to use the z-score, not the t-score. So that's going to be equal to, let's see, it's going to be equal to 1.151.4 plus or minus the z-score for a 95% confidence interval, which we know from the table is 1.96, times my standard error, which is equal to 6.6. Okay, so now let's say I want to calculate a 99% confidence interval. Well, the z-score that we use for a 99% confidence interval, we remember it's going to be 2.58, right? So everything else remains the same, 151.4 plus or minus 2.58 times 6.6. And since this is a bigger z number, bigger z-score, when I multiply this out, it's a bigger margin of error. We're subtracting a bigger number from 151.4 and subtracting and adding. So this becomes a wider interval than the 95% confidence interval. And that makes sense. If I use a wider interval, I'm more confident of actually capturing the true population mean between the two of these, which is really what I'm after. And a 90% confidence interval, again, we know is equal to 151.4 plus or minus. And now the z-score for that is going to be 1.64. In previous videos, I think I've gone through where we got these numbers from, or in class, where we got these numbers from, which is really from the z table, okay, times 6.6. Okay, so, and that's going to be a narrower confidence interval than either the 95 or the 99% confidence interval. And the reason why it can afford to be narrower is because we're willing to accept a bigger chance, less confidence that we've captured the true population mean, and willing to accept a bigger chance that we would be wrong. So we can have a narrower range here because there's going to be more chance we're going to be we might miss the mean in that case. Okay, let's move on to the next one. Okay, calculate the 99%. I think we just did that. Calculate the, let's see, did I do that? That same problem? Yes. 90%, 99%. Good. Sorry if I'm making you dizzy there. Up. Did I just do something wrong? 7.6. Let me go back here. I'm glad people show up to this because if they didn't show up to it, I wouldn't know when I do stuff wrong. What did I do here? 6? Oh, you're right. It's 7.6. 35. Yep, 7.6. 7.6. 7.6. 7.6. Great. Thank you. Sorry I didn't see that sooner. Jack, thank you, Janitha. You saved the session. Okay. I would have felt so guilty if we signed off and we didn't correct that. Okay. Okay, let's see. Good. I like that because it means you're paying attention. I appreciate that, especially this time of the morning. I'm not a morning person, so trust me, I would have slept till noon if we didn't get together and do this. Okay, calculate the lower 95% for all zombies populations and standard deviation. I think I lost something here. Calculate lower 95% population standard deviation. No, oh, okay. Yeah, let me see where I've gotten to here. 90%, 99%. And then the next question is, calculate the lower value for the 95% confidence interval for the mean cholesterol level for all zombies when the population standard deviation is not known and it is estimated by the standard deviation of the sample. Okay, now you had to repeat the above study. We should start up here. Repeat the above study without assuming the population standard deviation is known. In other words, you got the standard deviation from your sample. It's not that you were told what the population standard deviation is. as it turns out to be 38, okay, from the sample itself. So your sample mean was 154.1. In other words, not the population mean, sample mean. Your sample standard deviation was 38. Now your sample size is 25. So now we're going to start again. We're going to work with the t-score now instead of the z-score. Why? Because we don't know the population standard deviation, so we're forced to work with the sample standard deviation, and our sample size is relatively small. So the first thing that we're going to have to calculate is the standard error. Okay, so our sample size, let me get a fresh piece of paper. So our sample mean is 151.4. I'm going to go back and check these in a second if I get them wrong. And our standard deviation is equal to 38. Okay, so then our sample size is equal to 25. Okay, good. So I think I got all of those correct. Okay, sample size 38, 154. Yep, got them all right. Okay, so now we're going to calculate our confidence interval if we only have this sample that I've just described, if I only have that to work with. Okay, so x bar is equal to 151.4, standard deviation is 38. I know in order to calculate a confidence interval for this mean that I've gotten from this sample of size 25, I need to set up my calculations as x bar plus or minus. Well, now I can't use the z-score, so I have to use the t-value that represents the confidence interval that I'm going to work with. Not only the confidence interval, but also the sample size that I'm going to work with. And we'll see how that works in a second. Times our standard error. I still need to calculate a standard error. So our standard error is normally, optimally, is standard deviation of the population over the square root of n. Since I don't know what it is, I'm going to use the only approximation that I have to work with, which is the standard deviation of the sample, which approximates it. May not be exactly the same. In this case, I think it's I made it the same just to make things simple. But that's going to be. But normally it might not. It's not going to be the same. Okay, so it's going to be. Actually, we're going to wind up with the standard deviation for the sample over the square root of n. Okay, 38 over 25, that's square root of 25, which again, 5 into that is going to be 7.6. So our standard error is equal to 7.6. So now, this standard error is based on the standard deviation of the population, of the sample rather than the population. So that introduces an extra element of error in here. So if we use the z-score, we won't accommodate that extra variability that's introduced by not knowing the population standard deviation. So the t-score, the t-distribution, actually accommodates that extra level of uncertainty. Okay, but we need to look that up in order to decide what that number is. Okay, so let's look. Our sample size is 25. So we know our t is going to be, there's two things that are going to determine the value of t. That's going to be the level of confidence and I should get in a habit of block text here. The level of confidence is going to, and the sample size. The bigger the sample size is, the better our standard deviation is as an estimate of the standard deviation. So the t-value, which increases this margin of error, the smaller the t-value can be with the bigger sample size. So sample size is important, just as important as the level of confidence that we want, 95% or 90%, and so on and so forth. So let's go to our t-table. See if I can't find it here. Okay, and here's my t-table, I think. Yes. Okay, let's look at our t-table here. So our t-table gives us, instead of giving us the areas for every possible percentage of the normal distribution, like 81%, 0.8097, what area that represents, and what area the z-score of 1.93 represents. Instead of giving us all of that information, this table only gives us the information that's pertinent to solving these confidence intervals. Okay, so for instance, it gives us the confidence, the t-scores that we need to calculate confidence intervals for 95%, 99%, and 90%. Those are the ones you're going to use the most. But this one in particular, also gives you 80% confidence interval, 98% confidence interval, even a 99.8% confidence interval. But notice how big, how the more confident you need to be as you go across, the numbers get bigger, because as you want to increase your level of confidence, you've captured the true mean, that you have to make the margin of error bigger so that your confidence interval is wider, right? So as you go across here for a higher level of confidence, yeah, these t-scores get larger. But now as you go, let's go focus on 95% for now. Right now, as the sample size, degrees of freedom is really sample size minus 1, right? As your sample size gets larger, your t-score gets smaller, because the bigger sample size is, the bit more confidence that you have that you've estimated the standard deviation appropriately, and the narrower the confidence interval, the smaller the margin of error, narrower the confidence interval can be as you get into a bigger and bigger sample. And notice that as you get into really big samples, 60, sample size 60, 80, 100, 200, 300, you get closer and closer and closer to knowing what the true population standard deviation is, and using a t-score which represents 1.96, or in other words, the same as the z-score. So if you think that a 30 is a good enough, close enough, some people say, well, 30 can be considered a big enough sample to just use 1.96. Well, what you're doing there is, instead of using 2.04, which you should use, you're using 1.96 to make it simple and quick. You don't have to go to a table, right? So if that's not too much of an error that you can tolerate, then I guess you could say 30 is considered a big sample. If you're more conservative, you may say to yourself, I consider a big sample 100. So I'm going to use 1 point, because I don't want to, if it's over 100, I'm not going to bother, using the t-table. I'm just going to use 1.96. So that introduces a little error, but some of that, at least in the preliminary parts of doing a calculations, you might be willing to tolerate that extra little bit of error. Now, when we start using next week, we're going to start going back to using SPSS and Excel to solve a lot of these problems. When we do that, well, the software has these tables built into it. So the software will almost never use the z value, right? They're going to use the value from your sample and apply the t-score automatically, because even if it's a sample of 300 and there's only a tiny difference than 1.96, it's just as easy for SPSS to calculate and apply that. Okay, let's go back to here and see what t-value we need for our sample size and our level of confidence from 95%. So I'm going to go down here to 24, and we need to use 2.064. So I'm going to go back here, and I'm going to say, okay, t for a 95% confidence interval, t has to be 2.064 instead of 1.96. We know our standard error is equal to 7.6, and we know our mean for our sample is 151.4. So our 95% confidence interval is 151.4 plus or minus 2.064 times 7.6. And our 99% confidence interval, well, again, 1.51.4 plus or minus our t-score times 7.6. Let's take a look at what our t-score is going to be for 99% confidence. For 99% confidence, it's going to be a bigger number, we know, because it's got to be a wider interval. So that's going to be that's quite a bit wider, 2.797. 2.797. 2.797. Okay, and for a 90% confidence interval, we would be substituting plus or minus. Let's see, that's going to be a smaller number now because we can afford to have a narrower margin of error. Now we can get this all from the same table. 24 degrees of freedom, 1.711. Okay, and in every case, times 7.6, added and subtracted from 151.4. Okay, and notice in every one of these cases, 95, 99, 90%, the t-score is always bigger than it would have been if we used the z-score. 1.96, 2.58, 1.64. Okay, so I think, let's see how much, I think that answers most of the questions there. Uh-oh, I got a question mark. How do you know to use 24? Oh, wow. That's an excellent question. And uh, I'm tempted it's kind of complicated why we use degrees of freedom this way. We're gonna see this come up a lot in statistical calculations, the use of degrees of freedom. Remember when we calculated the variance, when we did the raw first week, when we did that raw calculation of a sample and calculated the mean, and then we calculated the difference between each value and the mean, and then we squared it, and then we added them all up together and called it the sum of squares, and then we took the sum of squares and we divided it by not n like an average, but n minus 1. We even used the standard deviation. We even use the degrees of freedom there. We divide it by n minus 1. There's a reason, a mathematical reason for doing that. But for the moment, just consider that that the degrees of freedom really represent the number of choices you have within a sample. So if you have one number, you really don't have any choices. You only have that one number. If you have two numbers, you have two possible values. If you have three numbers, you have two choices besides that first one. So for the moment, I wouldn't worry about that. I'll see if I can put together or articulate a better explanation. But let's not get hung up on that for right now. We do not have questions for those confidence interval. Even without having those specific questions, I just wanted to make sure we understood that that's how we'd go through this process. During lecture, they used 15. I'm not sure. 50. What was 15? Used 15 for what was that? The t-score. Oh, I'm not sure I remember what you're referring to in the examples. Oh, okay. Well, it's going to be it's going to be based on the sample size, right? In this case, the sample size was 25. In that case, I guess what was the sample size 15, or was the degrees of freedom 15? Oh, the sample size was 16. So we used a t-score of 14. We used the degrees of freedom then was 15. So that's how we would look up our t-score for that particular. It's because that's the sample size. Sample size also impacts the values. That would have been for a 95% confidence interval. We would have used a t-value of, if the sample size was 16, we would use a t-value of 2.13 for 15 degrees of freedom. Okay, let me go back there because I did get kind of a little, went off on a little bit of a tangent because I gave you more than what was in that example, I guess, right? Okay, they just asked for a 95% confidence interval, but it doesn't help, doesn't hurt, because now we understand that for each different level of confidence, all you're doing is changing the t-score. Okay, yes, depends on the sample size, exact sample size and your level of confidence. Yeah, T tables. I think the T table's there. I believe the T table is posted on Blackboard. You know what I'm going to do? I'm going to make a separate folder under the assignments. I'll post an announcement. I'm going to make a separate kind of reference folder. Maybe I'll just make a tab on the side called reference material and put in all of the tables. So in case I forget to put it next to the homework or in the same thing as the homework, that'll make it easier for you to find. And to be honest with you, I mean, you could also just simply do this. Watch this. Okay, if I ever forget to give it, t-tables. Oops. Okay, t-table. Okay, let's see. Why does it do that? T-table. We do a search, and I'll just go to images. And let's see if I can't find a good one. Here we go. Here's a t-table right here. Okay, so here we go. Here's the degrees of freedom and so on and so forth. They're like all over the place. But I'm going to make sure that we have a tab on the side with reference material. I think it's going to come in handy in the future too. I think that's a good. I'm glad you brought that up. Okay, last question here. Okay, based on careful study of Night of the Living Dead and other zombie movies, it appears that zombies are predominantly male. A random sample of 100 zombies from Halloween weekend zombie movie marathons, and I'm sure we're going to see plenty of that this weekend. Personally, I stay away from them. This is a former student, by the way. This is one of the students that didn't do well in statistics. That's what happens to you when you don't do well in statistics. Okay, so that's another reason why you should study hard when you take this course. So, based on a careful study of Night of the Living Dead and other zombie movies, it appears that zombies are predominantly male. Random sample of 100 zombies from these movies was taken, and we found that 58 of those 100 sampled zombies were males. What's the point value for the proportion of male zombies? Well, the point value, the equivalent of the average, but with a binomial variable like male or female, right? The point value is 58 out of 100, or 0.58. 58% of the zombies are males. So the question is that true? Is that true that there are more male zombies than there are female zombies, which is, I guess, the opposite of the population in New York, right? It's more females than males in New York. Okay. Well, is it true that that's the case? Well, what's the margin of error, 95% margin of error for the true proportion of male zombies in all zombie movies? Well, we only sampled 100 of them, so we don't know what the true proportion is, right? So let me go over here and get my paper. Okay, let's get a fresh piece of paper. So, let me get that. So 58 out of 100 are male, right? So our P cap, right? P cap represents the proportion of males in our sample is equal to 0.58, right? What we're really after is P, the proportion in the whole population of zombies. We only know what we know about a sample size of 100 zombies. Okay, so we know we can work with P cap as a point value, as a same way we work with the mean, and we can calculate a standard error, and then we can calculate a confidence interval. Now, with proportions, the way we calculate the confidence interval is we take the square root of P, the population proportion of male zombies, times 1 minus P over N. Okay, now again, we don't know what P is, right? We only have an estimate of it from our sample size of 100, which is a decent sized sample, right? So we're forced to use P cap in this formula. Okay, just like we were forced to use the standard deviation of the sample instead of the standard deviation sigma when we were working with only a sample and not knowing anything about the population. So this is going to be equal to 0.58 times 0.42 over 100, and we take the square root of the whole thing. So I'm going to go down here and calculate that. .58 times 0.42 equals, divide that by 100, right? And that's the whole inside of that square root, and I'm going to find the square root of that. Square root of that is 0.049. I'm going to round it off. Again, I like working with Excel, so I don't have to round stuff off. But for our purposes, I'm going to call it 0.49. 0.049. Okay, that is my standard error. So now I'm going to say I need to build a confidence interval. And our confidence interval, just like it was when we worked with means, is going to be equal to P cap plus or minus some value We don't know the population proportion, so that value is going to have to be a t-score, right? It's a relatively large sample. I'm going to use t here for now, okay? But it's such a large sample, and we have a rule that when we're working with a proportion, right, that we have to have a sample size of at least 30. Sample size always has to be at least 30. And not only does sample size have to be at least 30, but each side of the sample has to be greater than 15, has to be at least 15 or greater. So we're never going to wind up, the only time we wind up with 15, just 30, is going to be if it's exactly 15 and 15. But I mean, normally it's going to be, it's going to be, it's not going to be 10 and 25. That wouldn't work for us because it's less than 30. Okay. But let's see. So even if this were the proportion, 25%, we would have to sample at least twice, at least 50% more people. So maybe 20 and 60. So we'd have to get a big enough sample size so that both sides of our binomial are greater than 15. So most of the time it's going to be even bigger than 30. So in that case, Jesus, it's a large sample. When we're working with proportions, if we stick to the rule that our sample size has to be large, we're going to stick with Z most of the time, okay, instead of T. Okay, you could use T if you wanted to. Wouldn't be anything wrong with using T and looking up the degrees of freedom and substituting that. That would be even more accurate. But for our purposes, we're going to say because when we work with proportions, we only want to work with large sample sizes. In that case, we're going to tolerate using Z instead of T. Okay, so plus or minus Z times our standard error, So if I do in this case 0.58 plus or minus 1.96 times 0.049. Okay, let's work this out. 0.58 plus or minus our margin of error. Margin of error is going to be 1.96 times 0.049. Our margin of error is almost 10%, 9.6%. So I'm going to clear my memory here. I'm going to put this into memory, clear this. So I'm going to put in 0.58 minus our margin of error is equal to 0.483. I'm going to call it 0.484. 0.484. And our upper limit for our margin of error is going to be 0.58 plus our margin of error. It's going to be 0.676. I'm going to call it 0.68. And I'm going to round this off to just 0.48. So 0.48 to 0.68 is our 95% confidence interval. Well, what does that tell you about our study? Can I say, and this is kind of a little bit of an advance on this coming week, can I say with 95% certainty, can I say that that zombies are predominantly male? In other words, that the true population proportion of zombies is greater than 50%, greater than 0.50 male? Well, no, I can't really say that, can I? Because it is possible that they could be 49% male. In other words, 51% female, because that would be within our 95% confidence interval. In order for me to reject the idea that zombies are not either equally male and female or more female, I would have to have had a confidence interval, be 95% certain that the true population proportion is greater than 50. In other words, would have had to come out to say 0.51 to 0.61. Because then I could say with 95% certainty, it's not something lower or higher than that. Not for certain, but 95% certainty. Okay, so I think that probably runs through it. I think that probably covers this question pretty well. Okay, you can't calculate the margin of error and so on and so forth. Okay, and so I think I'm hoping that as we go through more of these examples, that you guys will get a handle on this, and it'll help understand when you use the t-score and the z-score and so on and so forth. Okay, So I'll be seeing you on online if for you guys in the uh, in 610 or in person if you're in one of the other courses. So in the meantime, have a great weekend and enjoy your Halloween. Okay. Any last questions there before you log off? If I forget about posting that extra reference area there, let me know and I'll take care of that. We all good? Okay. Good night, guys. Okay, bye.